Okay, so the moment that we've all been waiting for, the moment that pretty much our lives have been gearing up to, and certainly everything that we've been doing the last couple of weeks have been gearing up to, is actually sketching the graphs of these functions. Okay, so it's something you've already done plenty of. Okay, you've sketched plenty of graphs, but obviously you started from just straight lines and quadratics in National 5 to cubics and quartics in higher. So we're obviously looking at slightly more complicated functions now. So a lot of the same kind of properties and processes that you've done in previous years are going to help you here, but obviously we've learned a few more techniques, a few more processes that we need to look at over the last couple of weeks that are going to be important for sketching the graphs of the functions that we do at advanced higher. So we're still going to find any x and y intercepts. Okay, we want to make them nice and clear on our graph. Determine any stationary points and the nature of those stationary points. Okay, we're still going to go through that whole process. But then obviously through advanced higher, we've learned a few other things, okay, based on the graphs that we've been doing. Okay, so we've never really had these in terms of the graphs that we've looked at in previous years, but we're going to find any non-horizontal points of inflection. We're going to find any asymptotes. We're going to investigate the behavior of the function near any asymptotes, basically to see what's happening in terms of those asymptotes. And what we can look at to help us get a better picture of what the graph looks like is we can determine if the function is odd, even, or neither. Okay, most of the time it's probably going to be neither. Okay, but if it is odd or even, it's just going to give us a better picture of what that graph looks like. As I said, when we did this, odd and even ones, you can actually use that to basically build up the second half of the graph. If you know what one half looks like and you know it's odd or even, then you can just work out from that fact what the other half is going to look like. Okay. So as before, as when we're sketching any kind of graph, any kind of function, these all need to be labeled nice and clearly, and they must all be shown if they are, if they do exist. So you pretty much have to go through the process to find each one for any kind of graph that you're drawing to establish whether they actually exist, and more important, well, if they don't actually exist. So if they don't exist, then obviously you don't need to draw them, but you need to go through the process to establish that in the first instance, okay? And then all of these things need to be labeled and shown clearly on the graph that you draw, okay? So straight into an example. So we're going to sketch a graph of f of x where f of x is equal to 2 over x squared minus 1. So that's the graph that we want to have by the end of all this. Okay, so it's nothing like what we've drawn thus far. We've kind of looked at the different parts of it. We maybe used this one in terms of asymptotes, etc. We've not actually gone ahead and drawn the full graph of it, okay? And in part B, we're going to use our answer to determine the values of k, for which the equation f of x equals k has no solutions, okay? The graph's going to tell us that. Okay, if we think about asymptotes and whatnot, it's going to basically tell us that. If we know what the graph looks like, then part B is going to be nice and straightforward, okay? Right, so we're basically going to go through that list that I just put on that previous slide, and we're going to work out whether those different things exist, okay, and obviously where they exist if they do exist. So the first one we want to look at is the intercepts. Nice and easy, it's the same as what it always has been. Okay, the intercepts are going to occur at zeros. So for the first one, if we want to establish where it crosses the y-axis, then x will equal 0, in which case we sub our x's for zeros. So it becomes 2 over 0 squared minus 1, which is just minus 2, okay? So that gives us straight away a point. It gives us the point 0, minus 2, okay? Right, you can make a list kind of the points to one side that you establish in each one of these stages, or if you've got all this work and if you lay it out nice and clear, and I know some of you are not very clear when you do your work, and some of you are fantastic at doing this in terms of making it nice and clear, but some of you might need to work on that because there's going to be lots of different stages here, lots of different things to find, and obviously when you come to actually draw this, you need to make sure you've put all of them in, okay? So y-intercept is at minus 2, and then we need to look at see if there's any x-intercepts. Okay, so if there are x-intercepts, then we want the function to equal 0. But because of the fact that it's 2 divided by something that will never equal 0, then the function is always non-zero, in which case there are no x-intercepts. Right, that in itself tells us something else. Okay, it tells us obviously that there's an asymptote, that basically the x-axis is an asymptote, but we'll establish that for certain in the later stages. So you want the kind of the specific proof. That's not enough. Okay, in terms of getting marked for this in an exam, we want to go that one little step further and say a little bit more about this. Okay. Right, so the next thing to look at is the stationary points, and obviously if we're going to find the stationary points, then we need to start differentiating. Okay, you could use the quotient rule for this, but it's probably easier actually to just use the chain rule. Okay, so this is obviously the same as 2 times by x squared minus 1 to the power of minus 1, and we can use the chain rule from there, in which case it becomes minus 2 x squared minus 1 to the power of minus 2 multiplied obviously by the derivative of the brackets, so times by 2x, and simplify it into that. Okay, if we make that equal to 0 to find our stationary points, okay, then we're going to have something, well, we have minus 4x over x squared minus 1 squared equal to 0, and it only equals 0 if and only if minus 4x is equal to 0, which occurs if and only if x is equal to 0, in which case there's a stationary point when x is 0, and if we work out what y equals when x is 0 by putting the 0 back into the original function, we get 2 over 0 squared minus 1, which is minus 2, and that in itself is a stationary point. Okay, so again, add that to your list, okay, or just make it nice and clear, underline it. You're going to have to come back to that to obviously put it onto your graph. Right, what we need to do at this stage is establish what kind of stationary point this is, and the best, quickest way to do that is to use the second derivative. Okay, so we've got our first derivative there, so to differentiate that again, we are going to need the product rule. Okay, we've got minus 4x and we've got x squared minus 1, so this is a kind of a long-winded product rule, this one. Okay, but obviously the derivative of minus 4x is just minus 4, so times by the rest of it, plus minus 4x times by the derivative of the other side. So minus 2 times by x squared minus 1 to the power of minus 3 times by the derivative of what's in the brackets, which is 2x. Okay, it looks horrific, but you can simplify it slightly into this. And obviously we use that to find the nature of this stationary point by substituting the x value in. So we've got our x value 0, so I'm going to substitute that into here. So it becomes all of that, which is just minus 4 plus 0, which is minus 4. And the fact that that's negative tells us that the stationary point 0 minus 2 is a local maximum. Okay, so a bit of a faff, I realize, all of that kind of process to find what the stationary point is and to find what kind of stationary point it is. Okay, so again, add it to your list. This is another point we're going to have to make clear. 0 minus 2, which is a local maximum. Okay, moving on. We're going to look at any points of inflection. Okay, we have to do this process. Okay, we have to establish if there are any points of inflection. And obviously this is non-horizontal points of inflection. Okay, we would have found any horizontal points of inflection through differentiation in a previous slide. But this is looking at non-horizontal points of inflection. And obviously to do that, we need our second derivative. Okay, and we take our second derivative and we make it equal to 0. So if you follow this kind of same order that I'm doing, it doesn't matter too much, but obviously we've worked out the second derivative already, so we can just use it and set it equal to 0 for this one. Okay, right, this is obviously the equation. It's not a very nice equation. If we're going to solve it, okay, we want to basically get rid of the fractions, and to get rid of the fractions, if we multiply 3 by x squared minus 1 to the power of 3, then we have no fractions. Okay, so it becomes 16x squared by itself, and then minus 4 times by the x squared minus 1, the extra x squared minus 1 that we multiplied by there, and that equals 0. Multiply out the brackets, careful with the negatives, simplify it a little bit, divide by 4, x squared equals minus 1 over 3, and x would therefore equal the square root of minus 1 over 3, which obviously we cannot do, so there are no real values of x for which x squared equals minus a third, in which case there are no points or non-horizontal points of inflection. Okay, and I realize that's a bit of a faff to find nothing, but we have to establish this. We have to make this nice and clear in our graph. Okay, so when we're drawing it, there will be no points of inflection. But it's more important to kind of get used to the different phases, different stages of this process of actually sketching the full graph. Okay, so we want to establish this. At some points there will be, most of the case there won't be, but we still need to go through the process in order to find out which one it is. Okay, so once we've done that, we're going to look at our asymptotes. So the roots of the denominator x squared minus 1 are x equal to 1 and x equal to minus 1, in which case there are vertical asymptotes at x equals 1 and x equals minus 1. Okay, right, what we're going to look at next is basically what happens either side of those asymptotes. Okay, because what we know, if we know there's vertical asymptotes, we don't know what's happening as we kind of approach that asymptote. Is the graph going to go up or is the graph going to go down? Okay, so what we're basically looking at as x tends to minus 1 from the left-hand side. That's basically what that means. Okay, so as the x values get closer and closer to this asymptote, this first one, minus 1, okay, from the left-hand side, so basically we're saying as it gets from minus 100 to minus 50 to minus 4 to minus 3 to minus 2, as it gets closer and closer to that, what's happening to our y values? Okay, so they tend to a positive big number. Okay, so if they tend to a positive big number, then basically what's going to happen as it approaches that graph on the left-hand side is it's going to kind of shoot up. So it's going to curve upwards, and got to get closer and closer, obviously, to that asymptote as it does, and never quite reach it. But it's going to approach it's going to approach from the left-hand side and then basically go straight up. Okay. Right, and basically as the x values, imagine if they're coming from the right-hand side, so as they're approaching this asymptote from the right-hand side, so from the positive values, f of x is going to tend to minus a really, really big number. So as the graph is kind of coming in from the right-hand side towards that asymptote, it's going to shoot down the way, okay? Right, we're going to do the same with the other asymptote at x equal to -1. So as x tends to 1 from the left-hand side, f of x is going to tend to -infinity, and as x tends to 1 from the right-hand side, f of x is going to tend to +infinity. Okay, so again, this is just building up a picture of what's actually happening with those asymptotes. It's all very well not knowing where the asymptote is, but what is the graph actually going to do either side of it? Okay, and obviously there's two options. It's either going to go up or it's going to go down. That's basically what that process is establishing. Okay, so that kind of gives us an idea of our vertical asymptotes, but our horizontal asymptotes. Okay, so again, this kind of goes back to the table that I gave you a couple of weeks ago. So we know that we'll have a horizontal asymptote because the degree of the numerator is less than the denominator. Okay. Right, so then we're just basically just shoving in x values. So as x tends to infinity, so if we get a really, really big x value, it's going to get even bigger when we square it, and then take away 1, it's going to still be really, really big, and then we're going to do 2 divided by a really, 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 really big number, in which case the whole function is going to get really, really, really small. So f of x is going to tend to 0, and as x tends to -infinity, okay, f of x is still going to tend to 0. Okay, in which case y equals 0 is a horizontal asymptote, right? We already knew that one. Okay, we knew that one from the first part when we were looking at stationary points. No, not stationary points, intercepts. Okay, because it had no x-intercepts, then we kind of established from that point that the x-axis, in other words, the line y equals 0, is probably going to be a horizontal asymptote. But we still want to go through this whole process just to prove it for absolute certain. Okay. Right, as x tends to infinity, f of x will be positive, and as x tends to -infinity, f of x will be positive. So that's again just giving us an idea of exactly what's happening with that asymptote. So basically, is the graph above the asymptote or is the graph below it? Okay. So the last thing to look at is there any symmetry? Okay, is it an odd function or is it an even function? Okay, so f of minus x is equal to 2 over minus x squared minus 1, which is equal to 2 over x squared minus 1, which is equal to f of x. Therefore, where the hell's that going? Oh, it's gone miles back. Right. Therefore, f is an even function. Right. What that tells us, therefore, is that it's going to reflect over the y-axis. Okay, and again, all that means is that if we know what the left-hand side of the graph looks like, it's going to be exactly the same, but reflected on the right-hand side of the graph. Okay, right. So, taking all this information, we've got our intercepts. We've got 0 minus 2 is obviously a y-intercept, but we have no x-intercepts. We have stationary points at 0 minus 2, which is a local maximum. There were no points of inflection. We had asymptotes. We had vertical ones at x equals 1, x equals -1, and a horizontal one at y equal to 0. And then the symmetry was that it was even, so it reflects across the y-axis. Right, taking all of this, just popping that over there just for a second. Okay, we can draw our graph. So straight away, boom, look, there it is. Okay, and obviously we need to make it nice and clear. So you can see, hopefully from this, there was only one intercept. It was 0 minus 2. So the only point it should be crossing any axis is at 0 minus 2. Right, we knew also that that point was a local maximum. Okay, so we knew it had to turn at that point. So it's a maximum turning point at that point. Okay, in which case from that point it must go down a way. Right, we also knew there were no points of inflection, so we didn't need to worry about that. So it should just kind of, only turn at that point really. And then we can put in our asymptotes. So we knew there was vertical ones, x equals 1 and x equals -1. So if we're kind of just focusing on this bit just now, and it's all we really know that's happening, it never actually crosses that line. So it comes straight down and comes straight down. This is all we've got at the moment. Right, there's a horizontal asymptote at y equals 0. So then we're basically looking at the left-hand side and the right-hand side of this line. Okay, we kind of already established this in the first bit, but what basically happened, if you remember when I was doing the asymptotes, what I said is as x approaches this line, x equal to -1 from the left-hand side, as it gets closer and closer and closer, it tends to positive infinity. So it's coming from here, and bearing in mind that the y and x axis was an asymptote. Okay, it's coming from really low down. Okay, and then it's getting bigger and bigger and bigger and bigger and bigger and bigger. As it approaches that asymptote, it gets really, really high. So it shoots off there. And the same idea with this one, as it tended to positive 1, so as the graph approached x equal to 1 from the right-hand side, so from positive values, again, it was above the asymptote. Okay, it got closer and closer to this, and then it got bigger and bigger and bigger and bigger. Okay. We also established what was happening down here. Okay, I looked at that as well, but it was this is kind of made clear from the fact that this was a maximum turning. Okay. And as you can see from what we've drawn, it is reflective across the y-axis, and that was given to us by the fact that it was an even function. Okay. Right, so the second part, so using our answer to determine the values of k for which the equation of f of x equals k has no solutions. So you can see from the graph that if k is between -2 and 0, okay, so for the y values basically between -2 and 0, there are no values of x. Okay, so for which f of x equals k. Therefore, f of x equals k has no solutions for basically between -2 and 0. So there's a solution at -2, and this is where you've got to be careful with your symbols. Okay, so anything bigger than -2 and less than or equal to 0, so it could have equaled 0, but anything less than 0 and anything or less than or equal to 0 and anything greater than -2, there were no solutions. Okay. Right, a lot to take on board there, I realise, a lot of sketching of graphs. You're lucky I'm only doing one example, but there are plenty of questions for you to get on with in the textbook, so have fun.